Hi, I'm Micah Swedberg, and I'm going to be doing the buckling calculations for the first stage of the Falcon 9. So the Falcon 9 is a two-stage rocket that launches satellites into orbit. It carries a payload on top of the second stage that's released by the first stage. That's all powered by 9 Merlin 1D rockets. And we can simplify this whole thing down to your basic case of a bottle rocket with just one point of thrust and a cone on top, and just one stage. And for calculation's sake, we can simplify this further and say that it is a hollow cylinder with some loads on it. So those loads will be thrust, that'll be drag, and weight. The cylinder will be of height h, of a diameter, and of a thickness. Now our thrust is going to be from 9 of these Merlin 1Ds, which have a thrust of 845 kilonewtons, which comes out to 1.71 times 10 to the 6th pound force of thrust. These can carry a weight of 50,000 pounds to low Earth orbit, and that is 2 of our 3 loads on our structure. Now drag, the third load, is much more complicated. Now we know that the maximum forces happen at max Q, which if we watch our launch videos, we know that max Q happens around 750 miles an hour for the Falcon 9, and that is the point that is just over the point that it has broken the sound barrier. This happens around 7 miles in altitude, when the temperature is somewhere around negative 65 degrees Fahrenheit, and the density of the atmosphere is 0.02179 pounds per foot cubed, and that's all at 7 miles of altitude. Now to find the Mach number, we need to find the speed of sound at 7 miles high. We know that A is equal to the square root of gamma RT. So at negative 65 degrees Fahrenheit, we're going to assume a gamma of 1.4. Our A comes out to 663.58 miles per hour. So our Mach number will be 750 over 663.58, which gives us a Mach of 1.13. So just over the sound barrier. So we know that our drag is equal to our drag coefficient times the density and the velocity squared over 2 times the area. But we can't just use these direct densities and velocities because above Mach 1, we're going to form a shock wave in front of our fairing. Now if we go to our normal shock tables, we can find that rho 2 over rho 1 is equal to 1.238. And our Mach 2 is equal to 0.882. So if our Mach is 0.882, then we can find our velocity as 0.882 times 663.58. That's just the speed of sound. That is equal to 585.28 miles per hour, which is 200 miles an hour less than the actual speed behind that shock wave. So our density 2 is equal to 0.02179 pounds per foot cubed times 1.238, which is equal to 0.02698 pound per foot cubed. And we can use those directly in that equation. Now to calculate the area of a fairing is some sort of oblong shape, but the tip of our fairing, the part that's actually going to encounter the air, is pretty close to a cone. We can see here that the length of the bottom of this guy is 1 7/8 inch, and the length from bottom to top is 1 inch. And we also know that Elon Musk, standing right here, he is 6 foot 2 inches tall. So if we use Elon Musk as a scale and measure this diagram, we can actually find the measurements of the area, of the surface area for this fairing. So if we're measuring it as a cone, then the surface area is equal to pi RL plus pi r squared. Now pi r squared is for this back end, and since that is not going to be wetted area, we don't need to calculate that at all. So all we need is this length. Now length will be this length, and this will be r and h. So length will be equal to the square root of r squared plus h squared, which will be 2.125. So our area is equal to pi times 2.125 times 1, which is equal to 6.68 inches squared. And then we just need to apply our conversion factor of Elon Musk's, and that'll be 451.6 feet squared. That is the wetted area. So our drag calculation is our coefficient of drag times density times velocity squared over 2 times area. This, according to some place that I found on NASA, is equal to 0.75 for fairings, times 585.28 miles an hour over 2 squared, times the density of 0.02698 pound per foot cubed, times our area of 451.6 feet. Now we have a few conversion factors that we need to throw in here. We also need to multiply by our g sub c, which is equal to 1 over 32.174. When you calculate all of that out, it comes to 104,643.3 pound force, which is right around 100,000 pound force with our assumptions and everything else that we've butchered in here. So we can go ahead and get a summation of our forces in our y direction, which will be equal to our total pressure. That'll be our thrust plus our weight plus our drag, which will be equal to 1.71 times 10 to the 6th plus 0.05 times 10 to the 6th plus 0.1 times 10 to the 6th, which will be equal to 1.86 times 10 to the 6th pound force. For our buckling calculations, we're going to be taking that hollow cylinder, the single pressure force that we calculated earlier, the length of 140 feet, that's how long the first stage of the Falcon 9 is, with an estimated thickness of 0.21 inches. That's thanks to at Cambrianera and at Mode Meagle from some forum at NASA. That's supposed to say forum.NASA spaceflight. So that would be equal to 0.0175 feet. We know we have a diameter of 12 feet, and that's given by NASA. Now we need an effective length, an area, an elastic modulus, a yield strength, and an IXX IYY. Based on our material, we know that the Falcon 9 is made out of 2195 T8 aluminum, which has a modulus of elasticity of 10 times 10 to the 6th psi and a yield strength of 51 times 10 to the 3rd psi. Now our pressure was given before, that's 1.9 times 10 to the 6th pound force, and our area be equal to pi times the inner radius squared minus the outer radius squared, which is pi times 6 squared minus 6 minus 0.0175 squared, which will come out to 0.65877 foot squared. We also know that our IXX will be equal to our IYY because of symmetry, so that'll just be an I, and that will be equal to pi times the outer diameter minus the inner diameter to the 4th over 64. So that would be equal to pi times 12 to the 4th minus 12 minus 2 times 0.0175. All of that will be over 64. That comes out to 11.8234 feet to the 4th. All right, to calculate our pressures, we have a P max that will just be our yield strength times our area. Real simple. And that is equal to 51 times 10 to the 3rd times 0.65877 foot squared times a conversion factor of 144 inches squared per foot squared, which comes out to 4.838 times 10 to the 6th pound force. So given this and that our pressure was 1.9 times 10 to the 6th, we have a safety factor equal to 4.838 over 1.9, which comes out to 2.6 safety factor for straight compression. Now for buckling, again, for symmetry, we have P critical X equal to our P critical Y, which will just be our total P critical, which is equal to pi squared times the modulus times moment of inertia divided by our effective length squared. Now our effective length for a free body, our effective length to be 1.2 times our length. So that would be pi squared times 10 times 10 to the 6th pounds per inches squared times 11.8 feet to the 4th over 168 feet squared, and that is 140 times 1.2. And that comes out to 6.93 times 10 to the 6th pound force of buckling, which when we divide that by our 1.9 times 10 to the 6th pound force load, we get a safety factor of 3.73 factor of safety. So there you have it.